Alright, so far we looked at the use of Newton's method in solving very simple kind of problems, like a kind of f of x equals 0 problem. Now we're going to take a look at using Newton's method for slightly more complicated kind of problems. So we're going to consider a system of nonlinear equations now. So let's suppose that we have the following equations. We have y minus 0.2 times e to the 0.2x plus e to the minus 0.2x equal to 0. And the second equation is going to be x squared plus 4y squared minus 16 equals 0. So that's an elliptic equation. Now we're going to give these both of these parts of the equation, both of the left-hand sides, they're going to be essentially vector valued functions. So we're going to say that f1, which takes an x and a y, is going to be defined as the following, and we're going to have the second function f2 of x and y defined as this. So let's actually draw this on a graph and see what we're actually trying to find out. So here is an improvised graph with the x and y axis. Now the second equation is something like an ellipsis, so it goes something like this. Obviously it's symmetrical, I'm not that good at drawing. And then the other equation, the first equation, would go through something like this. And what we're really interested in is this point here. We're interested in the point of intersection. We want to find out its x and y coordinates using, once again, Newton's method. So in order to apply Newton's method, what do we need? Well, first of all, we need a couple of guesses as to where this point is. So for example, I can say that x of 0 is going to be equal to 3 and y of 0 is going to be equal to 0.5. These are our starting positions, and these are the positions we're going to start from. Now remember that in this simple example, in the example of Newton's method for f of x equals 0, we had to take a first derivative. Well, now unfortunately both of our functions, f1 and f2, they're actually vector valued functions. And as a result, if we want to formulate some sort of statement with regard to their derivatives, it's not a simple case of differentiating. We're going to have partial derivatives, and we're actually going to build something called a Jacobian matrix. So this Jacobian matrix requires the partial derivatives of the function f1 and f2 with respect to either of the arguments. So we have to have 4 partial derivatives in total. So let's compute df1 by dx, and that's going to be equal to 0.04 multiplied by e to the minus, actually no, that's not a minus, multiplied by e to the 0.2x minus e to the minus 0.2x, and we're going to have the partial of f1 with respect to y. That's just going to be equal to 1 because here is the only y-related term and its derivative is 1. And then the partials with respect to f2, first of all, df2 by dx, that's going to be equal to 2x because the only term with x is the x squared here. And then the partial with respect to actually these should be 2's, so partial df2 by dy, that's going to be equal to 8y because once again this is the only term that contains the y. So now we have the 1, 2, 3, 4 partials, and we can build a Jacobian matrix out of them and calculate the determinant. So essentially what we're interested in is we're interested in the determinant, the Jacobian determinant for functions f1 and f2, and this is the determinant of the 2 by 2 matrix composed of their partials. So that's df1 by dx, df1 by dy, df2 by dx, and df2 by dy, like so. So we can now plug in those values that we have because we've calculated all 4 of them. So this will be the determinant of the following. So df1 by dx is this long thing, so that's 0.04 times e to the 0.2x minus e to the minus 0.2x like so. Then df1 by dy is a 1. The term here will be 2x, and this will be 8y. And after you calculate the determinant, so this times this minus 2x, we're going to get the following. So we're going to have 0.32y multiplied by e to the 0.2x minus e to the minus 0.2x, and this all minus 2x. So this is the Jacobian determinant. And now what we need to do is we need to find the delta x and delta y. So we need to essentially calculate the displacement, if you will. So delta x here is going to be defined as a rather long fraction. So I'm going to draw a rather long line here to accommodate it. So this is going to be minus f1 at a point x0, y0 multiplied by df2 by dy, once again at a point x0, y0, plus f2 at a point x0, y0 multiplied by del f1, there's a 1 in here, by dy, once again at a point x0, y0. Managed to run out of space. Okay, and down below, we're going to divide it by the Jacobian. So that's going to be the Jacobian of f1 of x0, y0, and f2 of x0 and y0. Like so. So if we plug in the actual values, we're going to get something like the following. We'll get minus 0.0258 times 4 minus 6, all divided by minus 5.7963. And that's roughly 1.053. And then we do the same for delta y. So let me move this up, and we're going to have delta y being defined. I'll do a longer line this time, knowing that we need lots of space. So this is going to be minus f2 at a point x0 and y0 times del f1 by dx at a point x0, y0 plus f1 at a point x0, y0 times the partial of f2 with respect to x, once again at a point x0, y0, all divided by the Jacobian at f1 of x0, y0 and f2 of x0, y0. So once again, we plug in the values and we get something like the following. Let's draw another line here. So we get 6.00, actually no, it's 6 times 0.0509 plus 0.0258 multiplied by 6 divided by minus 5.7963. So what we end up with is a value roughly equal to minus 0.0794. So now that we have the delta x and delta y, we can calculate the x and y values using the following terms. So essentially we define x1, the next iteration in our guessing for the actual x value, as x0 plus delta x. So that's going to be equal to 4.053. And then y1, which is defined as y0 plus delta y, is equal to 0.4206. So obviously the values of x1 and x2 or rather x1 and y1, which are obtained here, are not the true solution. Nonetheless, these values are expected to be closer to the solution than our initial guess x0, y0. So the solution process actually continues by then using x1 and y1 as the new estimates for the solution and determining new sets of delta x and delta y's that give x2 and y2. And these iterations, they continue until two successive answers differ only by an amount smaller than some desired epsilon value. Let's take a look at the implementation of multidimensional Newton's method in MATLAB. Then there is plenty of code here, so I'm going to take it slow in explaining what's going on. First of all, we're defining our functions f1 and f2. And then what we're doing is we're using the symbolic toolbox to actually differentiate these functions against x and y, so we're getting the first derivatives for the first and second function. Now what's happening afterwards is we're getting the Jacobian, and the way that it works is we get the determinant in symbolic form, but then we're using a function called MATLAB function. Now what this function does is it basically turns a symbolic calculation into a function which takes a bunch of values, because we cannot directly invoke the determinant as a function. So we have to call this MATLAB function thing. And MATLAB function is actually not that great because it takes only the arguments which you actually have defined as symbolic variables. So for the determinant, we know that x and y are pretty much going to be there, but if you were to evaluate some of these derivatives, you'll get a constant, for example, and that would lead you to have a function with no arguments. So for having the functions of the first derivatives, what I'm doing instead is rather complicated. I'm basically taking the symbolic evaluations that we've had, I am substituting the arguments, so basically I'm having functions take x, and y. I'm substituting those instead of x and y, and then I'm calling the eval function to actually give us a numeric value, because otherwise you'll end up with fractional values and whatnot, and this isn't great. So it's a bit roundabout way of defining these functions, but once you've defined them, what we're doing is we're defining the initial guesses, so the initial guess 10 and 0.5, and we're defining the error tolerance that we're generally happy with. And afterwards we perform the actual calculation, so we get the Jacobian first of all, then we get the delta values, we calculate the x and y values that we've got from this method, and then we compare them against the actual values. So we're essentially looking at the error, we're looking at how much the result has changed over the last iteration. We print this out, and if the error is smaller than the tolerance value we specify, then we simply stop executing by invoking the break. So let's actually run this. As you can see, even though we asked for 5 iterations, and that's exactly what we've got. And you can see the error here. It's slowly going down with each number of iterations. So this is how you use multidimensional Newton's method.